Hello, it's vintage time here. Got a nice piece of vintage equipment. It's a fairly simple thing. We've got the Heathkit Digital Design Experimenter here. Got it secondhand. This thing's older than I am, so and it came with a circuit already breadboarded up, but it's a fairly straightforward little thing. Got the manual here, which I've scanned in, and I will hopefully get that posted. And I just skimmed it, and from what I could gather, this came as a kit that you put together yourself. And the other thing I love about vintage electronics, get this instruction booklet here, which has the pictures of the unit, but also full schematic. Not that there's a lot in there, but it's nice to have. Then on the back side, a couple little pictorials there showing you, I guess, where the obvious parts are and how to be testing it. But the nice part here is that they give you right here this outline of the board with a bunch of different places to take test voltages on, so that you know if there is something wrong, help with troubleshooting. Which is kind of nice. Not that it would be difficult to troubleshoot this, but seeing as how it is, you know, sort of a simple experimenter kit, it's probably would have been marketed more towards beginners. So a little better organized. We'll just take a quick look at the schematic here and the different features it has. So there's these four data switches here, and they're just simple slide switch. And if we look at the schematic, all they do is they connect the these terminal blocks here either to ground or to 5 volts. And the 5-volt rail, it's connected through this 470 ohm resistor here to protect them from a short. There's nothing on the ground side, so of course if you hooked something up and came back to one of these with something that was hooked directly to the power, then you'll short it out. Next they have these logic switches here, which are just a momentary switch. And if we look on the schematic up here, they show them as a pair of push-button switches, and each one goes into some flip-flops here made with NAND gates, so they'll be latched and debounced through that. And each one you have the output, and then you have the inverse output as well. Next, there's some clock modules on here. One is this line source, and what this is supposed to do is there's a ground and then an output, and this is supposed to output a square wave at the same frequency as your AC power coming into the thing. So if you have 60 hertz, then it should give you a 60 hertz square wave, and you know, if it's off a bit, whatever frequency you have, you should get on there. Next is a simple timer up here, and it's selectable between 1 hertz, 1 kilohertz, and 100 kilohertz. And just take a look here, and it's fairly simple. It's just a 555 timer. And then this selection switch here, you're simply switching in different sets of capacitors. So your different timing capacitors, and then the output is buffered through a NAND gate as well. And so you get the clock, and then you get the inverse clock. And I can't remember exactly what it is. I'll have to look in the manual for the duty cycle. And also on the schematic here, we've got this is the line source clock. So there's power coming in here from the transformer through 10K There's half bridge rectification with this diode, and then you're feeding that into this transistor, and then the output of that is then buffered as well. So next you got these logic indicators, which are just a bunch of LEDs with Darlington pair transistors. They're not an actual Darlington transistor. There's two discrete transistors in it. So it's the same circuit duplicated 4 times. The other part to this, last section, would be the power supply, which has plus 12, minus 12, and plus 5 volts. And the 5-volt rail is really simple. They're simply filter cap coming in. They don't show one on the output, but there should be a small cap in there. And it's just a 7805 linear regulator. The 12-volt, however, is a discrete solution. So it's fairly simple with current limiting on both positive and negative rails, and there's a trim pot in there so you can trim it in and get the voltage bang on. So that's about it. So I'll unplug her and open her up. And there we go. We're in. So there's the back side of the board. Nice, nice vintage electronics there. So let's just move this down a bit. So up here we've got a little box, and as you can see, that's just got the AC mains going in, and the mains from the transformer going into there as well as these wires for the switch. And then that way you just keeps it in there, I guess, to try and keep it a little bit more safe. Although, as you can see, you got your mains with the switch, and as you'll see when we flip it over, they showed a neon lamp for the power indicator. So you got your mains voltage right here on this PCB up in this top corner, and right here we've got this filter cap. So not the kind of thing you get away with doing now. So we gotta admit that whoever purchased this kit and put it together, they did a nice job on the bottom here with all these wires running into the switches. How they nicely along here bent up. Nice job. I would have bent these a little bit just to leave a little bit of elevation. You see there how the insulation slightly melted, so you have that chance of shorting them out. But let's just see what else is holding her down. Oh. Always one more screw. Okay, that should be it. So there's our front cover, comes right off. And just before I flip it over, you can see the capacitors here. So that's the selection for the frequency for the clock on this thing. So we flip it over. Here we go. This all was the front of the PCB. And here's all the components basically up here. Other than the filter caps that are mounted on the back side, and things like these capacitors that are just flying off the switch there. So then you flip it over. There's the neon lamp that I was talking about. So you got your mains right here, and then there's that's either going to be the plus or minus 12 volt pass transistor there. So as you can see, there's not a lot. I mean, the whole circuit is essentially crammed into this area up here. So we take a look here and just sort of compare it with the schematic here, which hopefully I can get this scanned in a few segments there and patch it all together and get this posted along with the manual. So we've got 4 pairs of transistors here, and if you look at that, there's 3 resistors for each pair. So that's obviously the Darlington pairs for these logic indicators. There's your only 8-pin chip on the board, so that'll be the 555 timer. A couple of these resistors will be probably tied into that, and as we saw, the timing capacitors were all soldered onto the switch here. Got the 2 full bridge rectifiers there. So I'd say this over here would be the 5 volt regulator. I find it interesting they have it marked BCE on the silk screen here, base collector emitter, and then next to it they have IC1 instead of all the rest of these transistors are all marked Q. So then these 2 guys here will be the quad 2 input NAND gates that are one of them will be used for these 2 logic switches here for the latching. Then the other one is used to buffer the output of the 555 and the line clock this line source clock here. So not much really to see. I mean, it's interesting. You got this huge heatsink on the 7805, and then a couple small heat sinks on these pass transistors here for the plus minus 12. We'll take a quick look here, but obviously they're going to be dissipating more heat there, so they needed the bigger heat sink. Oops. Forgot which page the specs were on. So just quickly look it up here in the table of contents here. Specs are on 41. So yeah, so plus and minus 12 volt rails can each output 100 milliamps. The 5 volt rail, however, can put out half an amp. So, and for the the clock here, they're saying the output frequency is plus or minus 20%, and the duty cycle is supposed to be 45%. So, yeah, since there's not a lot in here, I mean, it's put together beautifully for its time, and especially for being, you know, do-it-yourself kit. You know, there's a little bit of crust there left behind from the soldering, but I love these old tin boards. You know, there's something about them that just, I don't know, I kind of like it over the these new boards with the solder mask on. So, I guess we'll slap the whole thing back together. And maybe we'll turn it on again, and I'll pull out the scope and we'll take a few measurements. When I got this thing a couple of years ago, I did open it up, and there's the trim pot here for the plus minus 12 volt rails to adjust the voltage, and I had to trim them back in. They were way out of spec. I think they were putting out about 8.5 volts or so. So yeah, now that it's been sitting for a year or two, I guess we can take a look at that while we're testing things out and see how she works. Just before I finish closing this back up, I thought I'd pull off the cover here. So there's just a little tiny board in here with all the junctions, but the other thing I wanted to mention, I guess for the safety, I don't know, I haven't traced out. There is ground coming up around there, so there's probably a ground trace around this AC main stuff. But you'll notice there's this little wire here that comes in that ties the ground plane off the DC ground back up into the transformer and into mains earth ground. So just something to keep in mind if you're if you ever find one of these and you go to probe around on it, just keep in mind that it is Earth's main ground referenced. So careful if you you go to hook one up to an oscilloscope. Okay, so I got the oscilloscope hooked up here. It's a little bit tight. I can't quite get everything in shot, but so I'll focus mostly on the oscilloscope since we're interested in the waveforms here. So I got this hooked up to the clock here that's generated by that 555 timer, and as we can see in the 1 Hertz setting, it's just slightly below. Yeah, after it's traced out most of it, it's 956 millihertz, so just a hair under. Definitely a lot less than that plus minus 20%, and the duty cycle, well, I was reading 44. Not really sure with this measurement here. This some of these auto measurements and that I haven't played around with my scope too much. I just got it slightly before I had to move, so I think I had it to play with for about a week or so, which I was really busy, and then I had to pack it up, and unfortunately it's been in storage since. Anyways, we'll switch this up here, and there we go. So the 1 kilohertz setting, we're getting 1.028 kilohertz, so just a little over. Again, nowhere near that 20%, and duty cycle is 44. So we'll turn it up again. And at the 100 kilohertz here, we're seeing it's just a little bit under. I have to figure that all out in percentages, but it's not all that far off. It's nowhere near 20%. So I'd say the clock on this thing is, you know, plus minus 2-3% is what we're actually seeing, which is pretty good for something built back in the mid-70s. Now we'll just pop this probe here out. I'm going to sorry, I just gotta do this off screen, it's a little hard to see. And oh, that's a big fail. So I'll have to do a repair on this at some point, do some troubleshooting. But that, see if I can get the wire back in there. And you know what? I think I know what the problem is. Might have broken solder. This one connection's a little loose here, but that is supposed to be the line source, this square wave generated off the AC mains. I'll just move my scope back up out of shot here for a second. So this guy here, and I'm going to hold that up a bit. So as you can see, wiggly. That's not bad, but this here definitely feels a lot looser than, you know, any of these. These are all nice and firm. Not even the ground for this thing is a little loose, but both of these those terminal blocks there are both a little bit loose. And well, we got the oscilloscope out here. We'll just take a look at our rise time. So looks like we're around, let's say about 360 nanosecond rise time at the 100 kilohertz. So let's just see how it compares with the other frequency selections. There shouldn't be any difference because this is buffered through those NAND gates. So the NAND gates will be determining the rise time. And it looks like it's pretty close. I mean, yeah, so it's pretty consistent. About 360 to 380 nanoseconds throughout all of the cycles. So that's about the same there. That's, I just switched over and hooked the probe up to the inverse of the clock there. So, I mean, in theory, should be the same, but reality, things quite often don't match up with theory. So I'll have to take a look through the manual. I don't think it actually listed any experiments to do with the kit once you have it built, but definitely going to be ripping it apart again and do a repair video, see if I can't well, troubleshoot and repair. I think it's just this here, but who knows? Could be the transistor. It's a very, very simple circuit, so regardless of whatever the problem is, I'm sure I'll have no problems getting that fixed up and working again. Not really sure what I would use it for, but it'd be nice to have the unit restored and fully functioning. So take a look into that, and I'll have to see what I can come up with when I get my parts out of storage and that, and come up with a few simple circuits to breadboard up and use this thing. I mean, if nothing else, you have a solderless breadboard and you've got a power supply. But I'm sure I can figure out something to use these switches and the LED indicators for as well. Make a little bit better use of the. So now I'm a little bit more awake. I did a bit of research, and something that I had missed last night here is that there is pull-up resistors on all of these NAND gates, and I did a quick search for the data sheet, and something I didn't realize is that these are all open collector outputs, so they don't actually source anything. They only sink current, hence why they need these external pull-up resistors. So if one was inclined, you could change out these resistors for a slightly lower value to give you, or you should be able to get a faster rise time. So they're 1K right now, which means that they are, there's 5 milliamps going through them. That's having to be sunk when this is taken low. And you could have changed those to something like a 470 ohm, which would give you 11 milliamps, then they'd have to sink. So you would wind up heating up your silicone, a little bit more power dissipation there. If I was reading the data sheet correctly, which it was an old one that had been scanned in, so it was difficult to read, it wasn't exactly clear. But if I got it correctly, they recommended maximum current for these to be sinking is 16 milliamps. So at 11 milliamps, that means that you'd still have whatever you've connected to it could still be trying to source up to another 5 milliamps, and you'd be fine. The other thing was I took all the numbers here for the clock module here that that we found, and I said that they were a lot better than the 20%, which they are. It's a little bit off on some of them with the in terms of what they actually are. So at 1 hertz, at 20 plus or minus 20% means it'd be anywhere from 800 millihertz to 1.2 hertz. So the 954 millihertz is actually 4.6%, so not quite as good as the 2 to 3 that I was saying, but the 1 and the 1 kilohertz and 100 kilohertz are in that ballpark at 2.8 and 2.7%. Because everything is a 1 basically on this side, it makes it really easy to calculate the ranges, and then I did the worst here. So you just take the frequency minus what it actually was to find the difference, and because we're already dealing with 1, it's just a matter of moving the decimal over, and there you go, you got your 4.6%.